Can you guys hear me?
Yes.
Oh, cool. Yeah, I just didn't want to turn you into RCC too early. In class isn't that big a deal.
It is, somewhat of a big deal. Absolutely. I remember when I was in my last year of my bachelor's work, there was an instructor who, let's see, the second day that he was just plain missing, and they tried to call and tried to do all that stuff. They just called the police and said, could you go by his house and check on him? Because, he could be all kinds of bad. And he was, but for other weird reasons. Turns out he was an alcoholic. But anyway, that's another story. So I know you guys have been working on this stuff, and that's great. I know it can be kind of tough. I did not want to leave you guys on your own about this stuff. So I do want to make sure we talk about it. And I did, if you haven't seen it yet, I did go through and move the homeworks for 6.5 and 6.6 to Thursday. So we've got some time to talk about those things. Again, I know you guys have been working on them, so hopefully we can spend some more time in kind of an answering questions standpoint, as opposed to going through the whole discussions, but I'm happy to go through most of those discussions. There are good things for us to talk about, but the more familiar that you guys are with it from the work that you've done on your own is going to help speed that up. And we certainly have to talk about 6.6. 6.6 on inverse functions is a really important section. So I'd love Wednesday and Thursday, probably. We'll talk about that. I also moved your test as far as I think our schedule can sustain it. I was going to do it Thursday, but I thought, hey, why not Friday? You don't have to worry about testing centers or anything. But if that Friday day is problematic for you and your schedule for any reason, let me know. And we can move that around and make sure that works. I also moved the review. That is optional, but so you can practice it and play with it. I even changed the date down here. So we'll talk more about how the test is going to go procedure-wise as we get closer to that Friday. But hopefully having those homeworks moved should give you guys some more time to play with that. And I want you guys to have time to play with that with us discussing it. Let's see, if I don't know, you probably hadn't used any late passes with them yet, but if you have, I can give those back to you. Just let me know if you did, and I'd be happy to do that.
Hey, Matt.
Yes, ma'am.
What time is the test due on Friday?
It'll be end of the day. So it'll be open from morning all the way through end of the day. Like the quiz was supposed to be. Let's see. Oh gosh, lots of people here today. That's great. Dan, nice. Hi, Dan. Porter, okay. Oh, and I did hear you guys did a study session together, which is wonderful. So, I do want to do this example with sine. I know you guys have been working with cosine, and there are some questions that came up with cosine, and we'll talk about that. And maybe even secant and cosecant. But first things first, one of the big things I recommended for you guys was to write out what our amplitude, period, phase shift, which we'll talk about today. Again, most of you guys have been playing with it, but it does need some talking about. And that lift, or if you prefer, a vertical shift. I think your text likes to call it a vertical shift. So the amplitude was the absolute value of the outer coefficient. So whatever's being multiplied by your trig function, its absolute value is our amplitude. So our amplitude there is just the +3. I often make a note. If it's negative, I'll write the amplitude is 3, but put a little note that says flip, just to remind myself or try to remind myself to flip it. Our period for sine and cosine, our natural period is 2 pi. So to find our period, we're going to take our 2 pi and divide it by that compression factor. So this is how much we're being sped up by. So we've got to divide that out. So that's going to flip while the pi's cancel. So it's going to give us a period of 8 units, whatever those units are for x. So if x was, say, time in hours, it would be 8 hours. Phase shift we'll talk about in just a second. I want to do the lift first while we're, on the subject. So that lift is nice. It's just the constant that's being added to the trig function. So it's just going to have a lift of, 1. But if you prefer y equals 1 is going to be our equilibrium point. So that's going to be where our center line is. Questions about any of that before we talk about the big one, the phase shift?
Yeah, for B or T as you have it, didn't we need to get the pi over 4 outside the x? So shouldn't there be an exclamation point for x minus d?
No, but there can be. And actually, let me talk about that in terms of phase shift.
Okay.
Because this B, that period being the natural period of 2 pi divided by that B, whether it's factored out or not, that B is the coefficient of that x. So whether you're in this form or that other form, that pi over 4 is what's being divided by that 2 pi. But that issue does affect the phase shift a lot.
Okay.
So the issue that comes up with the phase shift is that one might want to look at this pi over 5, particularly with that negative, and might want to have it shift that way by pi over 5. However, ideally, you've got enough experience to remember, wait, that doesn't happen, because we remember everything on the inside happens backwards, right? So we probably have enough experience to go, okay, it's going to go that way, pi over 5. And it sort of will. The problem is that's not going to be the ending of our shift, because it's going to shift that way by pi over 5, and then the compression factor is going to happen. So that shift of pi over 5 is going to get compressed back by a factor of pi over 4.
Okay.
So if we just want to calculate that phase shift, it is that pi over 5, but after it's compressed by the pi over 4. So if you want to go out and calculate that phase shift separately, the pi over 5 multiplied by that thing's reciprocal, 4 over pi, the pi's cancel, we'll have a phase shift of 4/5. Now, some people like to do it this way. I like to do it this way. Take that constant and be sure not to take that negative with it. So grab that constant and then divide out the compression factor to find your phase shift. But you will see some people, and your book does a little bit of both, who instead of wanting this to be bx minus c plus d, notice the capital C there? They like to write it as y equals a sine times b times the quantity x minus c. Notice the oh so distinctive lowercase c.
Okay.
It is.
That's how I was used to it.
Yeah, and that's
I'll just have to.
Perfectly fine. And notice, if we're going to find this C, if we're going to factor out that B, we'd be factoring it out by dividing this constant by that B, right?
Okay. Got it. Thank you.
So some people like to do it in the actual equation. So we could rewrite this as 3 sine pi over 4 times x minus, we'd be factoring the pi over 4 out of that and get that same 4/5. And if you like doing it that way, go for it. Some people do. The reason I like to do it this way and use this form is because, frankly, people hand us equations in this form. They don't often wander around and give us things in that form. So I like to use, to see it from the perspective of how it's handed to us.
Right. Cool.
But really, either form is perfectly fine. Just be careful. So if you see it in this form, make sure you recognize that the pi over 4 has already been divided out and we don't have to do it again.
Yeah.
That's the only big issue. So with all this information, what does that mean our graph is going to look like? Well, the amplitude of 3 means we're going to go up and down 3 from our equilibrium. Our equilibrium point is going to be at that +1. So I'm going to draw my nice equilibrium at +1. That amplitude of 3 means we're going to go up to 4 and down to -2. So up to 4, down to -2. Now, normally for sine, we should be comfortable with the idea that sine normally starts at the equilibrium, travels upward through its wave to 2 pi, its normal period. So we would normally be starting at the equilibrium point and traveling upward, but that phase shift takes over and pushes us forward to the phase shift value of 4/5. Fair? And then how far does it go from there? Well, our period is 8 units. So it's going to go forward 8 units to, well, we could make it complicated, but how about just 8 4/5? I hate mixed numbers usually, but I'm going to accept it there. So that's where we're going to end. We'll often be asked for the quarter points. That's the points in between here. But the nice thing, this particular period is super nice because each of those quarter points will be a quarter of the period long. So each quarter of the period long. So each of those quarter points will be 2 units apart. So 4/5 plus 2 is, 2 4/5 plus another 2, 4 4/5 plus another 2, 6 4/5. So that's going to be our max, our back to equilibrium, our minimum, and then back to our equilibrium. So finding those quarter points by adding literally a quarter of the period to the beginning until we get back to the end is a really handy way to find those quarter points. Questions about any of that? Guys happy so far? The phase shift is usually a little bit of an issue, but once you get used to that idea of either factoring out the pi over 4 or dividing out the pi over 4, once you get used to that modification, it usually goes fairly well. And we can even look at it. What was it? 3 sine of pi over 4. There it is. X. Nope, not the X down there. That looks crazy. Minus pi over 5. Equals. Where did I go to school? There we go. So that's our equilibrium point occurring at 1. So that's our point there at 1, if I can find it. where is it? 1 occurring at 4/5. Oh no, 1. Our equilibrium point happening at 4/5 there. If I could get it to there, it is. The 4/5 1 going to that maximum at 2 4/5, 2.8, and a maximum of 4, and so on. The 6.8, that's the 4 4/5 down at -2. Cool. Now, some of you have been playing with cosine. And the first thing we want to do with cosine is just look at what its basic graph looks like. And we could do it by plotting points from our unit circle and all that. But the nice thing is we can also just graph it. Now, Shay, I think you put on the forums that you were having issues with the distinction between a cosine graph and a shifted sine graph, right?
Yeah, I had this issue last term where the phase shift of a cosine, whether it's positive or negative, and the phase shift of a sine, whether it's positive or negative, looked the same to me.
Well, the nice thing is that's good. They should look the same. Because if we remember our cofunction identities, the sine of pi over 2 minus x is equal to the cosine of x. Remember, if we change from an angle to its coterminal, not coterminal, sorry, from an angle to its complement, we change from the sine to the cosine. So these things are the same. We want to rewrite that for this context probably as sine of negative x plus pi over 2, or bring that negative, because remember it's an odd function, so we can actually factor out that negative sine of x, factored it out, so it's got to come out of that too. So that's the same as cosine x. So every cosine graph literally is a shifted, flipped sine curve. They're supposed to be the same.
On my open math, when you enter it, I have the numbers the same, but I'll have it as a cosine or a sine. Why is it marked wrong?
Well, that depends. First and foremost, if it told you to write a sine function, it's got to be a sine function. If it told you to write a cosine function, it has to be a cosine function. So if it told you and you used the other one, then it'll say wrong because that wasn't the reference it wanted. The second issue could be the phase shift on the sine will be different than the phase shift on the cosine because your anchors are different. So if you just change sine to cosine, then you haven't accounted for that shift. So every sine function should be able to be written as a cosine function, but the phase shift has to be adjusted. Fair? And actually, both the sine graph and the cosine graph are both referred to as sinusoidal functions because they really are the same. If you go into your calculator and look up regression, there isn't a sine regression and a cosine regression. There's just a sine regression because they're all sine curves. Fair? Now, one of the reasons we like having both of them is notice for the cosine curve here, it starts at its maximum. So usually if you're trying to figure out, should I be using the sine or the cosine, it really depends on whether or not you want to have your model start at its maximum value or start at its equilibrium value. And really in practice, you can pick either one. Fair? And the absolute best part of that is if somebody comes along and says, okay, I want you to graph, say, -2 cosine of 2x minus pi over, let's say 4 plus 3. Well, okay, we know how to handle all these things for a sine curve, but this is a cosine curve. But sine curves and cosine curves behave the same way. They just literally just start in a different place. So if we want to find, oops, I don't know what that did. If we wanted to find the amplitude, if we want to find our period, if we want to find our phase shift and our lift, which we will want to do, the best part is it's exactly the same as it is for sine. The amplitude is still what?
Absolute value of 2.
Well, technically the absolute value of -2, but you're right, 2. The period, our natural period, divided by the 2. So our period's going to be pi. Our phase shift, again, we could factor out the 2 if you prefer that, or just take that pi over 4, again, the pi over 4, not the negative, divided by the compression factor. So pi over 8. And our lift of 3. And even the beginning of drawing our graph is going to be the same. I'm still going to start with those same bounds. We're still going from our equilibrium point. Oops. So from that equilibrium point, don't know why that became orange, of 3, we're going plus or minus 2 from that. So up 2 to 5, down 2 to 1. That's going to be where our maxes and mins are. You don't need these dotted lines. I think I mentioned last week, you don't need those dotted lines. I like them because they give me a trough, be in that column or row or whatever, however you want to think about it. The difference is, instead of starting down here at the center, cosine wants to start at its max and go down. But of course, we have to account for the phase shift first, right? So we're going to go over to pi over 8. So it's going to be starting at that pi over 8 value and going out by pi to 9 pi over 8. Just added 1 pi, added 8 pi over 8s. So that curve is going to fit in that box. Fair? Now again, cosine, we'd normally start up here on top, but this negative, right, is going to flip us upside down. So instead, we're going to start here. Go to some midpoint that we'll find in a minute. Then go to our, what's now our maximum, back to that midpoint, and then back to that bottom. Fair? We want to tick those off. So we could say, okay, what's half, and kind of figure that out. But I like figuring out what that quarter period length is. The quarter period length is pi over 4. Or frankly, if we're in 8s down here, it's 2 pi over 8. So I'm just going to add 2 pi over 8 each time. Get those common denominators ahead of time. So that's going to make that happen at 3 pi over 8. Add another 2, we'll be at 5 pi over 8. Add another 2, 7 pi over 8. Add another 2, the 9 pi over 8 we were supposed to stop at. This quarter period trick is really, really handy for finding those values. And then just, boom, there goes our curve. So it's one of those things where it's like, but this seems like the same thing as sine. Why isn't it different? Knowing it's not supposed to really be different. If we wanted to, heck, if we wanted to do a sine instead, we could start a sine here and have the sine wave do that, right? It would have to have a phase shift of 3 pi over 8 instead, but we could do that. Heck, we'd even use Connor's notation. Where did Connor go? Connor left. We're just going to use his notation. That's okay. So if we wanted to turn it into a sine curve, y equals 2 sine. Notice I didn't keep the negative because it is going up from this point, right? If we wanted to do it from this point instead, we could keep the negative and go down. The coefficient of the x is going to be the same too because the period's the same. And I'm going to use those extra parentheses just to be able to plug in that 3 pi over 8 plus 3. So then 2 sine of 2x minus 3 pi over 4 plus 3. We could have solved this like we did over here too, knowing the phase shift has to equal the c over b. If we knew the phase shift was 3 pi over 8, and that had to be c divided by b, or 2, multiply both sides by the 2. It's the same process. You're multiplying by the same things. It's just, do you want to do it in the equation or do you want to do it off to the side? It's the same logic either way. So if you like the parentheses, use them. I use them when they're handy. I don't use them when they're not handy. So it's whichever way you want to go. So this sine curve, notice a lot of the numbers are very similar to this cosine curve, right? But they are different enough to account for which angle you're looking at, which perspective you're doing the problem from. So if somebody said, come up with a graph or an equation for this graph, well, we could end up with either one, and they'd both be right and interchangeable. But notice that -2 wasn't interchangeable. The pi over 4 is not interchangeable. Shay, does that help?
Yeah, a lot.
Okay, good. Anybody else have any questions about that example? Okay, then let's get a little nasty here. Let's say some rude person comes around and says, hey, I want you to graph y equals -3. I don't want another negative there because I want to use cosine. Well, let's stay with the negative. Cosecant, right, of pi over 2x plus pi over 5 minus, how about plus 2? So we already don't like this person, right? Whoever they are. They weren't me, whoever this was. And we got to go, okay, crud. We know how to graph sine and cosine, but how do we graph cosecant? I'll tell you the best thing about how we graph cosecant. It's technically the same way we graph secant, which shouldn't be a surprise. We don't graph them. That's it. You can leave. No, we don't do any of our logic on it because we have such good logic for sine and cosine. I'd rather use that logic. So we're going to pretend in green fairyland that instead we're graphing -3 sine pi over 2x plus pi over 5 plus 2. Because we know the relationship between these two parts. The relationship between those two should just be a reciprocal, right? So if we graph the sine function and then know how to manipulate that sine function into the cosecant, we can graph the cosecant without having to go through a whole new set of tools. Fair? So take a moment and do that. Figure out what your amplitude, phase shift, figure out what all that is for your sine function, and then we'll come back together and use that to graph the cosecant. Helix, what's your question? It's hard to respond to just a generic. Earlier I was confused that we couldn't graph. Oh, okay. I appreciate that. We can, but it's much easier to do it this way. And frankly, this is how one graphs, cosecant. So it's a little bit of a hyperbole. So our lift, still going to do the same. Nice tool. So an amplitude of 3. Put us down at -1. Center line at 2. Upper value at 5. I'm going to regret how high that is, but that's okay. Phase shift of 2/5. So that's going to happen at 2/5. And then our quarter periods are going to be 1s. That's super handy. Quarter periods are 1s. So we're going to be adding 1 to this. So that's going to go to, here, to 7/5. 12/5. 17/5. And 22/5. 1, 2, yeah. Which is 4 2/5, which is what we get if we add 4. It's always good to check. Sine is going to go through our equilibrium point. So it's going to start in our center. Now that negative means we're going downward, right? So we're going to go down to this minimum, back to the equilibrium, to that maximum, and then back to our equilibrium. And of course, it would then keep going from there and going from there. We could even go back, figure out where that point is. Back another 1 unit, so -3/5. Where's this next one going to be? Another quarter point, so 27/5 if we wanted to. Sometimes you'll be asked, graph something over 1 period, sometimes 2 periods. You should be able to graph it over as many periods as we're asked. So questions about any of that before we mess with it? I don't want to make sure where you guys are. So when you're happy with that graph, give me a thumbs up or something helpful. Nick, good. Dominic, good. Shay, good. It's not the same. It's built off of. So we do have to modify it. But we need this first. Martin, Porter, Dan, Keegan, good. Sam, what about you? Good so far. Okay. So we know the relationship between cosecant and sine is one of reciprocals. And that reciprocal is going to happen right, when we get the sine value, that sine value is going to become a reciprocal and then be multiplied by 3 and add the 2. So the 2 is still going to be a lift, so that lift of 2 still matters. That stretch of 3 still matters. We want to handle this reciprocal issue. So there's a couple places I want to focus on. One is this equilibrium point. At that equilibrium point, the sine function is outputting a 0. That 0 times 3 is 3. That 0 times 3 is 0, plus 2 puts us on the 2. So this equilibrium point happens when the sine is equal to 0. So that's when sine is equal to 0. This is when sine is equal to 0. Over here, that's where sine equals 0. So the cosecant is going to give us the reciprocal of that 0. But what's the reciprocal of 0? Felix said 0. It's not the reciprocal of 0. Zero is 0 over 1. So the reciprocal of 0 over 1 is 1 over 0, which is undefined. Because we can't divide by 0. 0 is 0 over everything, though? Yeah, that's true. So if it's 0 over anything you want, 0 over 7, its reciprocal is 7 over 0, which is still undefined. So what's going to happen at those equilibrium points is we are going to get that undefined becoming an asymptote. So all of those equilibrium points are going to become asymptotes, because the function's not defined there. Okay, let's look at the other key points. The other key points are these maximums and minimums. Well, the maximums and minimums happen when the sine is outputting a 1. Notice on the normal cosine and sine graph that those maximums happened when the cosine and sine reach its maximum at +1 or its minimum at -1. So right here, or let's use this one here, that point is occurring because the sine function is outputting a 1. The 1 times 3 is 3, plus 2 is 5. That's what's giving us that maximum point at 5. Same thing when the sine outputs -1. -1 times -3, well, yeah, -1, well, when that outputs a 1, the -3 makes it negative. That -3 plus 2 down to the -1. So these points happen when the sine function is outputting either a 1 or a -1. Well, what's the reciprocal of 1? Hopefully you're not gun shy now. That's the nice one. What's the reciprocal of 1? Dominic, you're mouthing it. Yeah, it's 1. So what's the reciprocal of -1? I'll jump in there for you. The reciprocal of -1 is still -1. Yeah. So these values don't change. So these values are going to be on both graphs. The difference is all these points in between are where the function is outputting something between 0 and 1, some number that's less than 1. Any number that's less than 1, when you take its reciprocal, it gets bigger than 1. So if you imagine when it's outputting 1/2, we know sine and cosine both output 1/2 sometimes. Its reciprocal is 2. Things like 3/8, its reciprocal is 8/3. Anything less than 1, its reciprocal is bigger than 1. So instead of curving down towards 0, these values are going to curve up towards infinity. The closer they get to 0, the closer their reciprocal comes to being infinitely large. Same thing down here. So when we graph cosecant, and the same with secant, frankly, we don't worry too much about graphing the secant or the cosecant. We graph the sine or the cosine, whichever its reciprocal is, and then essentially take those bumps and flip them out. Where it's at its equilibrium, we drop asymptotes. Where its maxes and mins parts are the center of that rotation, and we flip them out. Then we erase the green because we're not in fairyland anymore. And people wonder how the heck we did that. And we go, it's math. So, you know, we don't tell them. No, we tell them because we want everybody to know math because it's beautiful. So just like with cosine, everything we learned about graphing sine translates over to graphing cosine. Once we can graph sine and cosine, we can graph cosecant and secant from our sine and cosine curves just by flipping them out. All that we have left to do is the slightly different looking one, which is tangent. Before I let you go today, let me give you guys one of those, and let's do a secant just for completeness here. How about y equals, how about 1/2 secant of, what do I want here? Something fun. How about 3 pi x minus, ooh, that'd be fun, 4 pi. Oh, 4 pi, yeah, fine, 4 pi doesn't matter. Plus, sure, why not, 1/4. I don't know why I'm giving you horrible numbers because it's the last one of our day. And they're not terrible, terrible numbers, but they a little bit not what we're used to. So figure out what you should be graphing instead at first. Find the amplitude, period, phase shift, and lift for that new function. Graph it, and then flip it out. We'll even draw it and see what it should look like while you guys do that. Yeah. We go to Green Fairyland. You guys are going to be talking to somebody later and go, oh, I know how to graph those. You go to Green Fairyland. As I said last week, I do really recommend that you guys write out, my amplitude is this, my period is this. So period is going to be, what, the 2 pi divided by 3 pi, so 2/3. write out your phase shift. It just, that way, if your graph looks like something bizarre, I can look and go, okay, the graph might be crazy, but at least we know, I can tell what they were thinking. I can tell, you showed me you could find the pieces and that you knew what you were looking at. Just something went wrong when you were trying to graph it. So I highly recommend doing that in some nice, clear way. I'm going to put that at a quarter. Up, down a half. There. I'm just stalling while you guys work on it so I get to draw pretty pictures. And now phase shift of 4/3 and our period of 2/3. So our phase shift is, I didn't want that. Our phase shift of 4/3. And then our period of 2/3. So it's going to go out to 6/3 with a halfway point at 5/3. So that's kind of tight in there. That's okay. I know you guys have to go soon. So we're going to be trapped in there. That should be a lot wider, but let's do another one. Go out to 8/3. Heck, we can do a bunch of them. Go out to 10/3. But we're starting, what's a cosine? So we start on top. Go through equilibrium. Go to the bottom. Go back through equilibrium. Go on top. That was one. See if I can erase that. Here we go. So, and then it's going to do it again. It did hit that, I promise. And then it's going to go through that again. And of course, come down there. We could go back to 2/3 if we wanted, and 0. So it's going to 2/3 to 0. Notice this big phase shift did push us a lot this way, but we, do those rotations and we'll get back to that starting point. But once we've done all that, again, these equilibrium points will become our asymptotes. So all of those equilibrium points become asymptotes. Notice you don't see the asymptotes on the graph. What you see on the graph is just the flipped version of all of these curves. I am aiming my asymptotes to be there, but whether we draw them or not, we know those asymptotes are there. And, however many of these you want to draw. Again, if you're asked to draw it in a particular range or asked to draw it over a particular number of periods, you should do that. But the more you practice doing sine and cosine, the easier and easier it gets to do secant and cosecant. How does that feel? Got any questions about that? Does that seem nice and reasonable? Secant and cosecant always look more terrifying, particularly if you try to graph it on a calculator and you're zoomed way out and you go like, I'm going to become a history major because ew. But if you stay zoomed in, it's not too bad. Oh, it's just a bunch of little parabola looking like things. They're not actually parabolic in shape. Parabolics aren't asymptotic, but they do kind of look that way. And it's just that same curve flipped upside down. Nice thing to do is just take that and change it to cosine. That's the cosine curve. And we just flipped it. Take that curve, make it secant. Flip. So tomorrow, I want to look at tangent and I want to look at modeling scenarios. So do look over tangent if you haven't already. Look over graphing tangent. The more you can come having graphed tangent before, the faster and nicer that will go. So go fight with tangent. It really is based on a lot of the same logic. Our period shift is going to do the same thing. It's going to divide our period by that b. The phase shift is going to be the same. The lift is going to be the same. The amplitude is technically the same, even though we almost completely ignore it for tangent. We'll talk about why. But all the pieces do exactly the same thing. They just modify a different basic shape. So sine and cosine had one shape. So these are the modifications to that shape. Tangent has a different shape, but the modifications are the same. So play with that a little bit, and we'll talk about that and some modeling questions tomorrow. Anything you guys need before you trundle off? We will talk about inverse functions absolutely Wednesday and Thursday. We'll absolutely talk about inverse functions. They're very important. Okay, if there's nothing else, then you guys have a wonderful day. And again, I appreciate your thoughts and your patience.